What if I told you that the light hitting your face right now began its journey long before humans ever existed? Not years ago, not even centuries ago, but tens of thousands of years ago, deep inside a blazing furnace at the heart of a star. This is the story of our sun, how it was born, how it works, and how it silently powers every living thing on Earth. Before the sun existed, there was nothing here, no Earth, no planets, no warmth, no light. There was only a vast, cold cloud drifting through space, made mostly of hydrogen and helium, with tiny traces of heavier elements. But those heavier elements, like carbon, oxygen, and iron, weren't created in the Big Bang. They were forged inside ancient stars that lived and died long before our sun was born. When those stars reached the end of their lives, they exploded in massive supernovae, scattering their contents across the galaxy. That means every atom in your body was once part of a star. In a very real sense, you are made of stardust. For millions of years, this cloud drifted quietly through space, unchanged. Then something dramatic happened nearby. A massive star exploded in a supernova, sending a powerful shockwave racing through the galaxy. When that shockwave slammed into the cloud, it acted like a cosmic push, compressing parts of it and forcing matter closer together. Wherever matter gathers, gravity begins to take control. Slowly at first, and then more rapidly, regions of the cloud began collapsing under their own gravity, forming dense pockets of gas. These pockets became the birthplaces of stars. Our sun began as one of them, a growing concentration of gas known as a protostellar core. At this stage, there was no light, no fire, no nuclear reactions, just a dark, dense ball of gas slowly collapsing inward. But as it shrank, something important was happening. The particles inside were getting closer together, colliding more frequently, and moving faster. With each collision, the temperature rose, and the pressure increased. Eventually, the core became so hot and dense that it reached a critical threshold, about 10 million degrees Celsius. At that point, hydrogen atoms began to fuse together instead of bouncing apart. They combined to form helium, and in the process, a small amount of mass was converted into energy. This is described by Einstein's famous equation, E=mc². Even a tiny amount of mass can produce an enormous amount of energy when converted in this way. In that instant, the sun ignited. A star was born. From that moment on, the sun entered a delicate balance. Gravity continued to pull inward, trying to collapse the star, while the energy produced by nuclear fusion pushed outward. These opposing forces reached a stable equilibrium, allowing the sun to shine steadily for billions of years. This balance, known as hydrostatic equilibrium, is what keeps the sun from either collapsing or exploding. But the energy produced in the sun's core doesn't reach the surface immediately. In fact, it takes an incredibly long time, anywhere from tens of thousands to hundreds of thousands of years. That's because the sun is extremely dense, and the particles of light, called photons, can't travel in straight lines. Instead, they bounce around in all directions, constantly being absorbed and re-emitted by the surrounding plasma. It's a slow, chaotic journey, like trying to find your way out of a massive, crowded maze without being able to see. By the time these photons finally reach the surface of the sun, they have lost energy and transformed into the visible light we recognize. Once they escape into space, however, the journey becomes much faster. It takes only about 8 minutes for sunlight to travel the distance from the sun to Earth. So the light you see today began its journey deep inside the sun long before human civilization even began. And yet, this is only part of the story. Because around this newly formed star, a spinning disk of gas and dust was taking shape, a disk that would eventually form planets, moons, and everything we know. From that cosmic debris, Earth would emerge, and billions of years later, life itself would begin. As the sun continued to shine, the story of our solar system was only just beginning. Surrounding the young star was a spinning disk of gas and dust known as the protoplanetary disk. This disk formed naturally as the original cloud collapsed, like a spinning ball of dough flattening into a pancake. At the center sat the newborn sun, while everything else stretched out around it, slowly orbiting under the influence of gravity. Inside this disk, countless tiny particles began to collide. At first, these collisions were gentle, allowing bits of dust to stick together through static electricity and weak forces. Grain by grain, these particles grew into pebbles, then rocks, and eventually into massive objects called planetesimals, some stretching hundreds of kilometers across. Over time, gravity took over again, pulling these bodies together in a chaotic process of collisions and mergers. Not all regions of the disk were the same. Closer to the Sun, temperatures were extremely high, so only materials like metal and rock could survive. This is why the inner planets, Mercury, Venus, Earth, and Mars, are small, dense, and rocky. Farther out, where temperatures were much colder, lighter elements like hydrogen and helium could remain intact. Here, massive gas giants like Jupiter and Saturn began to form, growing large enough to capture enormous atmospheres. As these young planets formed, the early solar system was anything but peaceful. It was a violent place filled with constant impacts. Massive collisions reshaped entire worlds. In fact, scientists believe that Earth's moon was created when a Mars-sized object slammed into the young Earth, blasting debris into orbit that eventually clumped together to form the moon. Events like this were common, and they played a crucial role in shaping the planets we see today. During this time, Earth itself was transforming. In its earliest stages, it was a molten world, a glowing sphere of liquid rock constantly bombarded by asteroids and comets. But as the chaos slowly settled and the rate of impacts decreased, the planet began to cool. A solid crust formed on the surface, and volcanic activity released gases that built up an early atmosphere. One of the most important changes came with the arrival of water. Some of it may have been trapped within Earth's interior and released through volcanic eruptions, while some likely came from icy comets and asteroids crashing into the planet. As temperatures dropped further, water vapor condensed into liquid, forming the first oceans. For the first time, Earth had the key ingredient for life. Meanwhile, the Sun continued to grow stronger and more stable, providing a steady stream of energy. This energy would become the driving force behind everything that followed. It warmed the planet, powered weather systems, and eventually fueled the chemical reactions that led to life itself. Somewhere in those early oceans, under conditions we are still trying to fully understand, simple molecules began to organize into more complex structures. Over time, these structures became capable of replication and evolution. Life had begun, quietly, invisibly, but irreversibly. From that moment on, the connection between the Sun and life on Earth became inseparable. Every breath you take, every plant that grows, every drop of energy that moves through ecosystems, all of it can be traced back to the nuclear fusion happening deep inside the Sun. And yet, this balance is not permanent. The Sun, like all stars, has a lifespan. It is stable now, but it will not shine the same way forever. One day, billions of years from now, it will begin to change, and when it does, the fate of Earth will change with it. For billions of years, the Sun has remained remarkably stable, quietly fueling life on Earth without interruption. Every second, deep within its core, nuclear fusion continues to convert hydrogen into helium, releasing unimaginable amounts of energy. That energy travels outward, escapes the Sun's surface, and spreads across the solar system, reaching Earth in just 8 minutes. It may seem distant, but this steady stream of sunlight is the foundation of almost everything we experience on our planet. On Earth, that energy drives the climate and weather. When sunlight reaches the surface, it warms the land, oceans, and atmosphere unevenly. This uneven heating creates winds, ocean currents, and weather patterns that shape the environment we live in. Without the Sun, there would be no winds, no rain, no seasons, just a frozen, lifeless world. But the Sun's influence goes even deeper. It powers life itself through a process called photosynthesis. Plants, algae, and certain bacteria capture sunlight and use it to convert carbon dioxide and water into glucose and oxygen. This simple yet powerful process forms the base of nearly every food chain on Earth. The oxygen you breathe and the food you eat both exist because of sunlight. In a very real way, every living thing on this planet is sustained by the energy of the sun. Even the energy we use in our daily lives often traces back to the sun. Fossil fuels like coal, oil, and natural gas are made from ancient plants and organisms that once relied on sunlight millions of years ago. Solar energy, wind power, and even hydroelectric systems are all driven, directly or indirectly, by the sun's energy. It is the ultimate source behind nearly every form of usable energy on Earth. And yet, despite its importance, the sun is not a gentle place. Its surface is a boiling sea of plasma, constantly churning and erupting. Massive loops of magnetic energy can twist and snap, releasing powerful solar flares and bursts of radiation. Sometimes, the sun hurls billions of tons of charged particles into space in events known as coronal mass ejections. If directed toward Earth, these particles can interact with our planet's magnetic field, creating stunning auroras in the sky, but they can also disrupt satellites, communication systems, and power grids. Fortunately, Earth has a natural shield, its magnetic field. This invisible force surrounds our planet and deflects most of the harmful charged particles coming from the sun. Without it, the solar wind could gradually strip away our atmosphere, making life as we know it impossible. In many ways, Earth's magnetic field works hand in hand with the sun, allowing life to thrive while protecting it from the sun's more dangerous effects. As stable as the sun seems, it is slowly changing. With each passing second, it converts millions of tons of hydrogen into energy, and over time, this changes its internal structure. Very gradually, the sun is becoming brighter and hotter. The change is almost imperceptible on human timescales, but over billions of years, it will have profound effects on Earth. In about 1 billion years, the sun's increased brightness will begin to heat Earth enough to disrupt the delicate balance that allows liquid water to exist. Oceans may begin to evaporate, and the planet could become increasingly hostile to life. But this is only the beginning of a much larger transformation. Because the sun, like all stars, has a life cycle, and eventually, it will reach its final stages. What happens next will reshape the entire solar system in ways almost impossible to imagine. Billions of years from now, the sun will begin to approach the end of its long and stable life. For most of its existence, it has been quietly fusing hydrogen into helium in its core, maintaining that delicate balance between gravity pulling inward and energy pushing outward. But this balance cannot last forever. Eventually, the hydrogen fuel at the core will begin to run out. As the supply of hydrogen in the core dwindles, fusion there will start to slow down. Without enough outward pressure to counteract gravity, the core will begin to contract. But this contraction doesn't mark the end, it triggers the next phase of the sun's life. As the core shrinks, it heats up even further, and this increased temperature causes hydrogen fusion to ignite in a shell surrounding the core rather than at the center itself. This change has dramatic consequences. The outer layers of the sun will begin to expand enormously, causing the star to swell into what astronomers call a red giant. The sun will grow so large that it could engulf Mercury and Venus, and possibly even Earth. From the perspective of our planet, if it still exists, the sky would be filled with a massive, glowing red star, far larger and more intense than the sun we know today. During this phase, the sun's surface will cool slightly, giving it a reddish appearance, but its overall energy output will increase significantly. Conditions in the inner solar system will become unimaginably extreme. Any remaining traces of oceans, atmospheres, or life on Earth will be completely erased. The planet itself may be vaporized or torn apart by the sun's expanding outer layers. But just like before, this phase is temporary. Helium is far less abundant than hydrogen, and it will be consumed much more quickly. Once the helium in the core is exhausted, the sun will face a new problem. it simply won't have enough mass to generate the extreme pressures and temperatures needed to fuse heavier elements like carbon. At this point, the Sun has reached the limit of what it can do. With no new source of energy to sustain it, the Sun will become unstable. Its outer layers will begin to pulse and drift away into space, creating a vast, glowing shell of gas known as a planetary nebula. These expanding clouds can form some of the most beautiful structures in the universe, colorful, intricate patterns of gas illuminated by the fading core of the star. At the center of this nebula, the core of the Sun will remain behind, no longer undergoing fusion. What's left is a white dwarf, a small, incredibly dense remnant roughly the size of Earth but containing about half the Sun's original mass. A single teaspoon of this material would weigh tons. It will glow intensely at first, radiating leftover heat into space, but without any fusion to sustain it, it will slowly cool over billions, even trillions, of years. Eventually, the white dwarf will fade into a cold, dark object known as a black dwarf, a silent, invisible remnant of what was once a shining star. However, the universe is not yet old enough for any black dwarfs to exist, so this final stage remains a prediction of the distant future. And so, the Sun's story comes full circle. The material it releases back into space, carbon, oxygen, and other elements forged during its lifetime, will drift through the galaxy once more. Over time, that material may become part of new clouds, new stars, and new planets. Perhaps, somewhere far in the future, it will even become part of new forms of life. The same process that created our Sun will happen again and again across the universe. Stars are born, they live, and they die, but in doing so, they give rise to everything that comes after, including us.